Hey, Math 20s, this is the next lesson. So standard normal distributions. The big thing with this is z-scores. So hopefully you also have a data sheet with you. Actually, what we'll need at some point is the chart at the back of your book. So if you flip all the way in the back of your notes package, there should be a pretty giant chart that looks a little bit like this. We'll be using that a little bit today, but we'll do the physical way that involves the chart a bit, but I'll also talk you through the calculator stuff. So make sure you have your calculator with you. So how do I go away? So there's not another set of notes. We're just going to work through the statistics book for this one. So it says, as useful as the properties of normal distributions are, they are not quite good enough for some situations. So we're going to look back at that electronics store selling protective cases for an MP3 player that is 70 millimeters long. Suppliers B cases had a mean length of 71 millimeters and a standard deviation of 1.5 millimeters. And so the question is, if the lengths of the cases are normally distributed, what percentage of the cases from supplier B is shorter than 72 millimeters? So we're looking for everything shorter than 72 millimeters. So to answer similar questions in the last lesson, we sketched a normal curve. So again, your normal curve has the mean in the middle. And then we had those specific rules. So 68% of the data will fall within one standard deviation above or below. 95% of the data will fall within 2 standard deviations, and 99.7 will fall within 3 standard deviations, with those little tails adding up to that 0.3 beyond 3 standard deviations above or below the mean. So our target based on the question above was 72 millimeters. So if we look at our graph, so our mean was 71, standard deviation was 1.5, so 1.5 above the mean is that 72.5. So that 72.0 falls somewhere in between, right? It's between 71 and 72.5. So if we were to look at the area under the curve, it would look something like this, right? That's as nice as I can make it on the smartboard. So it covers off part of a standard deviation, right? It's not exactly on one of those lines, so we can't get those nice round numbers that we had before. We're kind of doing some estimating. So what we did is once we marked that data point of 72, we shaded everything to the left of 72 millimeters. Again, that's representing shorter than 72 millimeters. And then adding the areas of the bars. So the areas of the bars, sorry, I've got to scroll up, and I probably should actually erase all this scribbling that I've done now, or just put it over here. So the total shaded area, so we add that far left tail, so 0.15, that's this part, plus 2.35, that's this part, plus 13.5, you can see where that is, plus 34, plus whatever this would represent. So it's not 34%. So my estimate, so if that's 34%, I'm going to estimate that it's about 20-ish%. Because it's probably like slightly more than half of it. So I'm estimating that it's about 20%, because again, this whole bar is 34%, and it's definitely not the whole bar. So I estimated about 20%. So if I add all of those numbers up, about 70% of the cases will be shorter then 72 centimeters. So B says, how is this problem different than the ones in the previous lesson? The problem is 72.0 is in the middle of one standard deviation. So if 72.5 is one standard deviation to the right of the mean, again, the mean being 71, how many standard deviations is 72 to the right of the mean? So if we looked at that, so 71, 72.5, 72.0, it's about 2/3 of a standard deviation. So if we divided it in thirds, so 71, 71.5, 72, and 72.5, that's about 2/3 of the way between your mean and one standard deviation. So it's about 2/3 of the way. But we can't say it is 2/3 of the way, but since this box isn't actually, oh, made a mess. Since this isn't a rectangle, you see here that it's not a perfect rectangle because of, whoa, that's not a straight line. This area, see where I'm shading in here? It's not a rectangle, so we can't say that it's exactly 2/3 of the way, because that would be, if it would work if it was a perfect rectangle, but you can see due to the shape of the curve, it's not a rectangle. So it's not like we could take 34 and multiply it by 2/3. So 34 multiplied by 0.66666, which is 2/3, is 22.6 repeating. But that would only be if it was a rectangle. So we can't use that amount. It's a really good estimate, right? I estimated above about 20, right? I estimated that was about 20 out of 34, but this is probably a better estimate, but it's still not exactly right because that area is not a rectangle. So I think that's what it's kind of talking about on this next page. It says, the problem, since 72 millimeters is not exactly on one of the standard deviation divisions, only part of that last bar, so only part of the 34% is shaded. This is exactly what I had on the other sheet. So this part is the 50% below the mean. And then we need to add on that last little bit. So I'm gonna see if it will let me write on my screen. Probably not. Oh, because I'm using my, what will it let me do? No, it won't let me do anything I want right now. Maybe if I do it on here. I'm trying to do it on the trackpad. Whoops. Let's just pretend I'm a little bit better at drawing straight lines on the trackpad. So that represents this part of the last bar. So 50 and a bit. And again, I estimated that part of the last bar as, I don't know, something about 20%. So it's saying, what is the area of this last bit? And so this is what I was kind of representing previously as well. So this represents one standard deviation being equal to 1.5 millimeters. So if we divided it into thirds, that 72 is at 2/3 of the way. I guess we've kind of talked about all of this already. So this is our mean, so either as mu or x bar. This is our mean plus one standard deviation. And this is our mean plus a third. So 0.33 is a third. This is our mean plus 2/3 of a standard deviation. And so as it's saying here, this is all what I did on the front page. If that last bar was rectangular, why won't it let me? The shaded area would be 2/3 of 34%. So that's that 22.6 repeating that I got. However, all the bars have curved tops. So we need a method to find areas that fill only part of a curved bar. And luckily, we have a way to do that. So there is a simple formula for determining partial standard deviations. And so this gives us something called the Z-score, or the Z-score if you are American. I'll probably call it both because I can't decide. So the Z-score tells us how many standard deviations any single piece of data is above or below the mean. And so the formula, which you'll see if you look on that chart that's on the back page of your notes package, this formula actually is there. So the formula that I just put a box around is on the chart, but it doesn't define any of those pieces of information. So a Z-score, the way that we calculate it is we take our raw value, our piece of data, we take that and subtract the mean of the data. So again, you can see that sometimes we see it as mu and sometimes we see it as x bar. In this formula, it has it as mu. And we divide that value by the standard of deviation of the data. So that looks a little bit crazy because it's all letters and weird symbols, but you know this standard deviation thing. You know the mean. Yes, we have a different symbol, but you guys can remember two things in your brains, right? And then the raw value is just our piece of data that we're actually looking at. So using this formula in our example, we get, so this is using the formula. So our raw value or our piece of data would be the 72.0. That's the data point that we're looking at. We're trying to find out where it is on our normal distribution. So we'd go 72, that represents this x part. Subtract the mean, so the mean is 71, and we divide it by the standard deviation. That's right here as well. So 1 divided by, sorry, there should be a decimal here. 1 divided by 1.5 gets us 0.67 or something along that line, 0.67. So what this tells us, what this 0.67 is, it is how many standard deviations above or below the mean. So sometimes you can get a negative number because if we look at a normal distribution, I'm just flipped back a slide. No, I'm going to flip back 2 slides and then erase everything that I've scrawled. So if we were looking at like 68.5, what we would get when we calculate out that Z-score, so that's, see I'm flipping between Z-scores and Z-scores. When we'd calculate out that is we would actually get a negative value because that's the mean subtract standard deviation. So those are standard deviations below the mean. So if you get a negative number, it is fine. Don't stress out. So I want to show you, so keep this 0.67 in your brain for a second. We're going to talk about the calculator way, but I'm going to show you the physical way as well, because you do actually need to use this at some points. So flip to that chart on the back. I think, okay, I did put it here. So this just looks like the messiest, grossest situation ever, but it's just because people way smarter than me calculated this all out and made a nice chart, so I don't have to calculate it out. So we have two charts here. You see there's kind of a division in between. So these you see have all negative values here. So these are below the mean. The negative ones are below the mean. The positive ones, the second chart over here, are above the mean. So again, that answer that we got was 0.67. So the way that we use this chart is we want to find the corresponding part that says 0.67. So this has our ones, sorry, I'm pointing to it. This column here has our ones and tenths place, and then the column across the top has our hundredths place. So we need to scroll down to 0.6. So I just do this with my finger. So I'm looking for 0.6. And then in the hundredths place, I have 0.07. So what I want to do is go across and down to figure out this number. Hopefully you can see that fine. So the area under the curve that 0.67 represents is that 0.7486. So keep that in your brain for a second, or highlight it on your little chart if you need to. So 0.67 is again equal to the z-score. So then if you use the chart to find out the corresponding area under the curve, that gets us 0.7486. Was that the number? So 0.7486, which represents, so again, we talked a little bit about this yesterday, that we call the area under the curve equal to 1, which represents 100%. So 0.7486 out of 1 represents 74.86%. Sorry, there's not enough room for me to write all of those things, so they're kind of in the middle. So that's how we use the chart. That gives us the area under the curve. So that chart, it looks super cumbersome, and honestly, you'll use it a little bit, and you'll probably use 3 different numbers in the giant chart, and that's all you'll need, but all the numbers are there. So just as a little bit of practice, so peek at the chart right now. This isn't in your booklet or anything. If we got a z-score equal to 2.44, so looking in on that big chart, I'll flip over to it. If I got a z-score equal to 2.44, what area under the curve would that represent? So 2.44, so I don't have a negative, so I'm not using the chart on the left side, but 2.4 is right here, 2.44, so I need to go down and across. So 0.9927, which represents 99.27% of the data. So I'm just going to erase that. Some other ones that I just want to kind of show you. is what if we had 1.00? So 1.00, oh, yeah, and 2.00. And 3.00. Actually, this is not really going to help me out the way I wanted. Um, so 1.0, if we're talking about it. So remember we said that 68% of the data is within one standard deviation of the mean. I'm just going to flip back to this drawing. So one standard deviation, so that's a z-score, equals a z-score of exactly 1.00. So that would be this 72.5. So the area under the curve would be 50%, because that's this side of the mean, plus 34. So that's equal to 84%. And now if I flip forward again, so you see a z-score of 1.00 represents 84.13% of the data. So it's a little more precise than I give you as your 68, 95, 99.7 rule. We could do the same thing with 2. So if we figured out that we would be adding on 34 plus 13.5, we're going to get 97.5 in that case, but again, it's a little bit more complex. So this is how we use our z-scores. Remember that you can have a negative z-score though. So one standard deviation below the mean would be a z-score of negative 1.00. So one standard deviation below the mean, it kind of works in the reverse way. So you see that 1's down here, gets us 13.79% of the data is one standard deviation below the mean, or smaller, I guess is how I should phrase that. So that's how you can use the chart. So you need to calculate out the z-score. So you need to have the mean, the standard deviation, and whatever your raw data point is. But you will be able to use your calculator. So just on the bottom of page 30, it says mathematicians have determined how much of each bar is shaded for all partial standard deviations. Before calculators, these areas were recorded in a table, but your graphing calculators have that table programmed in. But again, sometimes you will need to use the table, so don't think your chart or your calculator can do everything for you. There are at least 4 different methods to access the tables in most graphing calculators. We'll look at the 2 of these in detail. So just up on the screen there, it says calculator method 1 using z-scores and calculator method 2 using raw data. So method 2 is faster. Method 1, you need to calculate the z-scores first. So we're still going to talk about both of them. I probably most of the time will use the method 2. So we have both sets of instructions here. I also have my Casio ones written down, but I haven't practiced them. So this one is for our TI users. So what you do, TI peeps, is you press second, so your yellow button or whatever color it is on your calculator, and then VARS. So it's just kind of below your up, down, side keypad. So when you press second VARS, you're actually looking at distribution, DISTR. And so what your screen actually shows, it says distr, and what have I done? Second VARS. Sorry, I'm having a, gotcha, sorry. I was looking at the wrong screen. So second VARS distribution. So you scroll down to number 2, it says normal CDF, and then it kind of opens a bracket and press enter. So now it should be on your main screen. It should say normal CDF and a bracket. And so the calculator now wants to know two things. It wants to know the z-score of the left side of the shaded area, or your lower boundary, and the z-score of the right shaded area. So it wants to know the z-score of this part and the z-score of this part. So the tail goes on forever. So there really is no left side. It should keep going on. It says since there is less than 15% in the tail, it's not really a big deal. If we use a number that is very small, we will include almost all of the shaded area of the right shaded area of the tail. And when the shaded area includes, when the shaded area includes the left tail, we need the lower boundary to be like a super small number. They use this, so putting in -1e 99 followed by 99 zeros, a super small number. You can put it in this way. You could probably just put in -10 should give you a close enough answer, but just you want to have a really small number. You can put in -10,000. You're going to see it's probably not going to be that different. This is just putting in the smallest number ever, not ever, but it's making a super small number. If you put in -10, it should be okay. So your calculator should say normal CDF. I'm just going to put -10, and then you put a comma. So the comma is just above the 7 on the TIs. So -10, comma. And then the z-score of our right boundary is 0.67. This is for the question that we had previously. Remember, we calculated out the z-score of that right boundary at 72 millimeters. Oh, 72. And then you got to close your bracket. Oh, I put in 72 instead of 0.67. And press enter, and the calculator will find the total shaded area between the two z-scores. So rounded to 2 decimal places, it's 0.75. I get 0.7485, but again rounded. So this is if you have the 2 z-scores. The nice thing is, we'll see some examples. If you have the 2 z-scores, it's super easy to use this one. The other one's pretty easy too. So Casio Peeps, I don't have the note right now for how to do method 1. I just have it for method 2. So I'm going to figure that out later, and then I can make you a little quick video or email you. You'll probably use method 2 most of the time anyways, so it's not a big deal. So TI people, same idea for method 2. So this is using the raw data. So you press second vars, which is distribution, and number 2. And now what we're going to do is we're actually going to be entering 4 things in order. You can't put them in the wrong order. Your calculator is not smart enough to know what you mean. So you put them in order. So the first thing you put in is the raw score of the left side of the shaded area, so the lower boundary. So the shortest cases we could have is, I don't know, 0 millimeters. So I'm going to put in a 0 and then a comma. And then it says the raw score of the right side of the shaded area, the upper boundary. So for our MP3 cases, that's 72 millimeters. So it's like the left side of it, the right side of it, then you put a comma. Next is your mean. So in that case, it was 71. Then you put another comma, and then you put the standard deviation of the data, which was 1.5. And then you close your bracket, and you press enter, and you get, again, rounded to 2 decimal places, 74, so 75 rounded to 2 decimal places. So give that a try. Casio people. So Casio to calculate areas under the curve. So you press menu, you go to your stat menu, which is number 2. I can write this down too if you want to make yourself a little note. So Casio Peeps, you go menu, then you press stat, which is number 2. And then you press F5 which is, it says the same thing. It says distribution or something like that above it. It just says dist, I guess. So you press F5, and then you press F1, which says norm above it, meaning normal distribution. And then you press F2, which says NCD. So again, it's looking for the cumulative area under a normal distribution, NCD. And now it gives you, it's kind of asking you some questions. So it says data. Oh, there's going to be a whole bunch of, I guess I got to do it on here. So where it says data, you're going to make that say variable. So you press F2. So now it says variable. And then you put in your lower boundary. So in this case, the lower boundary is 0. Your upper boundary is 72. Then the next one it says is standard deviation, so that would be 1.5. And then it gives you your mean as mu. Woo, too much. Your mean as mu, which for that example was 71. I don't know what save res means, but I'm just gonna assume it means nothing. And then you scroll down and press execute. And it tells us a couple different things. So Casio peeps, hopefully you've done that. If not, follow through again. So at the top, it says P equals 0.7475, which we would round to 0.75. Then it also gives us our Z-scores. So my lower Z-score, giving it a score of 0, is -47. That's pretty far. And my upper Z-score is 0.666 repeating, which we had already calculated out, right? We had calculated that that Z-score was 0.67. So those give us our two Z-scores. So that's how we put it in. It's a little bit of a process remembering, especially with Casio, where all of those things are. But once you've practiced it a few times, it becomes pretty, you remember it pretty quick. So let's keep working. So summary, summary for finding areas with partial standard deviations. And this is just what it's kind of saying. So we've already figured that out. So method 1 is using the two Z-scores. So you need to either calculate them out using this formula, or if you're given them, so that's just using your two Z-scores, or method 2, which is typically faster because you don't have to calculate out Z-scores. You put in your left raw score, your right raw score, your mean, and then your standard deviation. Casio's, you put it in a little bit of a different order, but yours tells you obviously which ones it would be. It tells you left boundary, right boundary, then it's standard deviation, and then it's mean. So that's all of it. Just so you know as well, this question doesn't have it, but you can also have questions where it says, like, what is the area under the curve between 2 points? So if we wanted to know how many were between whatever this is, 68.5 and 72. So this area that would be red, we can look at the area under that curve. So in that case, your left boundary would be whatever this line would be. I think I have a practice problem with that, but it's not always going to be all the way to the edge. Sometimes it will be like a Z-score that's not -47. Okay, then there's a little note about drawing it on your calculator, but let's just go to some of the practice questions. So we're still talking about MP3 players. I swear this is not getting old. So it says a survey has shown that most customers do not buy a case that is more than 1.5 millimeters shorter or 1.5 millimeters longer than their 70 millimeter long MP3 player. What is the probability that an MP3 case chosen at random from supplier B will have a length less than 68.5 millimeters and therefore is too short? So this is still dealing with supplier B. We're going to look at both methods for calculating it. So we have a raw score of 68.5 millimeters. This is looking at method 1. Again, Casio, I'll have to figure out if there's a faster way to do method 1, but I think that the only way you can get your z-scores is from that method 2, so you might just spend time only doing method 2. But just to talk about those z-scores again, so we have a raw score of 68.5 millimeters. Calculate the corresponding z-score. I notice that I keep saying z and z, and that's all right. So in order to calculate that score, again, you take your raw score of 68.5, subtract the mean, divide by your standard deviations. The standard deviation was 1.5 millimeters, gets us a z-score of 1.67. So the negative 1.67. So the negative indicates that 68.5 millimeters is 1.67 standard deviations lower than the mean, or to the left of the mean. So just keep that negative 1.67 in your brain for a second. I'm going to go back to that big fancy chart. So negative 1.67, so negative 1.6, 0.07. I just want us to keep this little number in our brains as well. So the area under that curve should be 0.0475 or 4.75%. Because again, negative 1.6, 0.07, we find where they meet, and that gives us our 4.75%. But we're talking about the calculator way, not the chart way. So the question asks us to find the area to the left of this. So we're sketching a curve that looks something like this. 1, 2. Sorry, I'm just confused. I don't know. Kind of ignore these ticks on the bottom because 1.67 would be here, I think, instead. This is a very confusing way that they've drawn this graph. But we're just looking for that area below our z-score of negative 1.67. So what we want to put in the calculator, since that tail goes on forever, is you want to make a very small number that will include all of the shaded area of the tail. So you can put negative 10 billion. I think still if you put negative 100 as the left end of the tail, or negative 10 even, should be good enough. And then negative 1.67. That will give us our shaded area of 0.05. Remember when I used the chart, I got 0.0475. I think that, sorry, 475. That's just rounded to 1 decimal place. So it says, therefore, the probability that a case chosen at random from supplier B is less than 68.5 millimeters is about 5% or 0.05. So that's the method 1 using z-scores, but we had to calculate out that z-score, so a little bit more work. Using method 2, so Casio people following those steps that I wrote down, TI people following the steps as they are here, is we put in our lower boundary, our upper boundary, and then our mean and our standard deviation. So again, the mean of the data was 71.0. The standard deviation of the data was 1.5. So our lower boundary, if we're talking raw data, we're not talking z-scores anymore because a z-score of 0 would be exactly the mean. So we put in 0, 68.5, 71.0 for the mean and 1.5 for the standard deviation. Again, Casio people, I think yours is in the opposite order for those last two, but it tells you which way it is, so you should be able to put them in. So once you punch all that in, we get 0.05. Same number, two different methods. Okay, so in a shipment, we're going to try question 2 here. In a shipment of 1,000 MP3 cases from supplier B. Why did we pick supplier B? Wasn't supplier A like way better for standard deviations? I think it was. This is silly. Yeah, we should have picked supplier A. Their standard deviation was 0.33 millimeters. Somebody's trying to save some money, I guess. So in a shipment of 1,000 MP3 cases from supplier B, how many could be expected to be within the acceptable lengths of 68.5 millimeters and 71.5 millimeters? Because as it said on the last page, so just under guided practice, it says the survey has shown that most customers do not buy a case that is more than 1.5 millimeters shorter or 1.5 millimeters longer than their case. So they want to see how many will fall in that range of 1.5 millimeters shorter or longer. That's where that 68.5 and 71.5 comes from. So we now have a range, and you see, looking at that picture that's on the screen or on your sheet there, is we now have a lower boundary for our raw data of 68.5 and an upper boundary of our raw data of 71.5. So I'm probably going to use that method 2. If you wanted to use method 1, you need to calculate out the z-scores for both 68.5 and 71.5, and then you can do that method 1. So all the power to you if you want to do both. So it's a sketch a normal curve and add what you know. They kind of did that for you. So using method 2, so maybe give this a little pause and try putting it in using method 2. So where you use your lower boundary, your upper boundary, and your mean and your standard deviation. So try punching that in and then unpause it. So hopefully you've put it in. Again, Casio folks, I hope that you put it in the right order, because I think, if I'm not mistaken, I could pull it up. I think that those are switched. So make sure you put them in the right order, because if you mix them up, your calculator doesn't know that you meant to say the standard deviation was 1.5. It just assumes that what you put in is right. So our left side is 68.5. Our right side is 71.5. The mean is 71.0 and the standard deviation is 1.5. So that gets us something along the lines of 0.58276. I don't know, you might not have saved all those decimal places, or about 58.3% if we converted that into a percentage by multiplying by 100. So that's not that many, right? If you're buying 1,000 MP3 cases and only 58% of them is considered acceptable, well, that means 42% of the cases are unacceptable. We probably are not going to save that much money buying from supplier B, because people are going to return a whole bunch of them for being incorrect. So, sorry, this part C is just on the last, or on the next page. It says this answers the proportion of all cases made by supplier B between 68.5 and 71.5 millimeters. For the actual number of cases in a shipment of 1,000 is if we took that 0.583 and multiplied it by 1,000, only 583 out of the 1,000 would actually be considered acceptable to customers. All right, one more and then I'm done, I promise. So, sorry, with that last question, if you wanted to do method 1, you would need to figure out the Z-score for 68.5 and the Z-score for 71.5. So a little bit of a process, but totally doable. So Nadim and Eva enter a charity bowling tournament. In the men's, so Nadim is a man and Eva is a woman, I guess. So Nadim bowls 124. The tournament average is 120 with a standard deviation of 4.0 points. In the women's tournament, Eva bowls 120. The tournament average is 116 with a standard deviation of 3.2 points. So the question, I guess, for C is who did better relative to the rest of the tournament competitors? So overall, like if you just compared Nadim and Eva, well, Nadim scored a higher score than Eva. 124 is higher than 120. But we want to compare them to the rest of the people in their tournament. So we need to calculate out the set scores for both Nadim and Eva in order to be able to compare them. So for Nadim, Nadim's raw score is 124. The mean for that tournament, oh, it's right here, is 120. And the standard deviation is 4.0. So 4 divided by 4 is equal to 1. So Nadim's Z score is equal to 1. Eva's Z score, so Eva's raw score was 120, the mean was 116, and the standard deviation of the women's tournament was 3.2. So Nadim's Z score, sorry, did I say Nadim there? I might have. Eva's Z score is 1.25. So if we just looked at a normal curve without any actual numbers on it, so the mean of both of their tournaments being represented right here, Nadim was exactly 1 standard deviation above the mean. So that's where Nadim's score would be versus the rest of his competitors. Whereas Eva was 1 standard deviation plus a little bit. So Nadim's score would have been this one here that I made wiggly. Do I keep saying the wrong name? I think I'm losing it. Eva's score would be 1 standard deviation plus a little bit higher. So you would say that Eva did better than the rest of the competitors because she has a higher Z score. Oh, I was like, is that all? But it seems like there's a lot more. So it says rounding your answers to 2 decimal places, determine how much better each did compared to the total number of people in their respective tournaments. That is, find the area to the left of each of their Z scores. So you could do this by the chart, since we have the Z scores, or by the calculator. Both are going to get you to the same answer. So you could do the calculator by method 1 or method 2 because now we have the Z scores for each of them. Or you could do it by method 2 by using your lower boundary, your upper boundary, whatever kind of works. So I'm not going to use the big fancy chart, but actually that would be pretty easy to use right now. I'm going to use my calculator. So Nadim, so putting it in the TI, again, Casio, you've hopefully got this down a little bit. So the lower boundary would be 0. The upper boundary or Nadim's score was 124. The mean was 120. And the standard deviation was 4. And for Eva, same thing. Lower boundary is 0. Her score was 120. The mean of her tournament was 116. And the standard deviation was 3.2. And so for those calculations, Nadim did better than 84% of the people in the tournament, or 84% of the data is on the left side of his. Eva did better than 89%. So again, those decimal places from these, Nadim's came out as 0.8413. Eva's came out as 0.8944. And so here are both of their graphs. So therefore, Eva bowled a better game compared to the competitors in her tournament than did Nadim did compared to the competitors in his tournament. All right, that's a lot. I'm praying that it recorded. Come on, baby, be recording. Yeah, 50 minutes, that's a long one. Okay, so you have practice questions on page 35 through 38. Make sure you do all of those and hit up the textbook for some additional practice. See you later.